Somewhere out in the deep universe, a galaxy is falling. Not drifting, not slowly migrating, falling headlong into a cluster of thousands of other galaxies, moving faster than sound can travel through the hot gas that fills the space between them. And as it falls, it is carving something that astronomers have been hunting for decades, a glowing arc of radiolight shaped like a bow and arrow, stretching nearly 1.8 million light-years from end to end. The researcher who spent 25 years studying objects like this saw the images and said he had never, in all that time, seen anything like it. And the person who found it first was not a professional astronomer at all. They were a student sitting on a hillside in the Himalayas, combing through telescope data on a laptop. The galaxy has been named RAD-BAARG. The name is a catalog designation, the kind of compressed abbreviation that gets assigned to newly discovered objects when there is no common name yet and the discovery needs to be filed. What that name does not convey, and what no name really could, is what this object actually looks like in the radio images that revealed it, or what it means for a decades-old prediction about how galaxies and space itself interact in ways no other tool had ever caught clearly enough to see. By the end of this video, you will understand what RAD-BAARG is, why its shape is impossible by the standards of everything we normally observe, what the physics behind it tells us about how galaxies live and die inside the universe's largest structures, and why the way it was found may be as important as the finding itself. Let's get into it. To understand what makes RAD-BAARG strange, you first need to know what a radio galaxy is, and what they are supposed to look like. A radio galaxy is a galaxy with an actively feeding supermassive black hole at its center. As matter spirals into the black hole, some fraction of that infalling material does not make it all the way in. Instead, it gets redirected by the black hole's magnetic field and fired outward in two narrow jets of plasma, one from each pole, traveling at velocities close to the speed of light. These jets plow outward through the surrounding space for hundreds of thousands or millions of light-years, eventually slowing and spreading into vast lobes of radio-emitting plasma, glowing brightly at radio wavelengths even when invisible to optical telescopes. From Earth, we detect that radio glow and use it to map the structure of the galaxy and its jets. The key thing about normal radio galaxies is their symmetry. The two jets emerge in opposite directions from the same central black hole, fed by the same engine, pushing through the same environment. One goes left, one goes right, and both spread into lobes of roughly comparable size and shape. When you map them in radio light, they look like two glowing teardrops on either side of a central bright spot, sometimes with thin, straight jets connecting them. Symmetrical, balanced, predictable. Thousands of radio galaxies have been catalogued over the decades, and almost all of them follow some version of this pattern. They are, in the language of astronomy, well-understood objects. The physics that governs them has been worked out in enough detail that you can model them with reasonable accuracy before you even observe them. RAD-BAARG does not follow this pattern. On one side of its central black hole, a narrow jet emerges and feeds into a vast sweeping arc of radioplasma, a curved structure that bends away from the galaxy in a direction that should not be possible if the jet were simply expanding freely through empty space. On the other side, the jet does not mirror the first. It twists. It bends into an S shape that distorts as it extends outward before eventually fading into a faint tail that trails behind the galaxy in a completely different direction from the arc. The two sides of this object look like they belong to different galaxies. There is nothing in the textbooks that describes an object with this combination of features, and the researcher who led the study, a scientist who has spent 25 years examining radio galaxies for exactly this kind of structural detail, had never encountered anything with a structure that matched it. The explanation for the shape is the explanation for why this galaxy matters so much beyond its unusual appearance. RAD-BAARG is falling into a galaxy cluster at supersonic speed. Not supersonic in the way we use the word to describe an aircraft, where sound travels through air at around 760 miles per hour, and breaking that barrier produces a sonic boom. Supersonic here means faster than the speed of sound through the intracluster medium, the hot, thin gas that fills the space between galaxies inside a cluster. Galaxy clusters are the largest gravitationally bound structures in the observable universe. They contain hundreds to thousands of individual galaxies, bound together by their combined gravity, and they are embedded in enormous halos of dark matter that extend far beyond the galaxies themselves. But the space between the galaxies inside a cluster is not truly empty. It is filled with a diffuse plasma of extraordinarily hot gas called the intracluster medium, heated to temperatures of tens of millions of degrees by the gravitational energy of the cluster itself. This gas is so hot that it glows in X-rays, and it is detected routinely by X-ray observatories as a cloud of emission permeating the cluster volume. It is thin enough that you would call it a vacuum by any earthly standard, with densities far below what even the best laboratory pumps can achieve. But it is not nothing. It has density, it has temperature, it has pressure, and it transmits disturbances at a finite speed. What most people do not appreciate about galaxy clusters is that they are not static objects. They are not just large collections of galaxies sitting in space waiting for astronomers to count them. They are actively growing. The universe is laced with a cosmic web of dark matter filaments, vast invisible threads stretching hundreds of millions of light years. And at the intersections where these filaments cross, matter accumulates into the knots we call clusters. Galaxies fall along the filaments toward those knots over billions of years, and when they arrive, they do not ease gently into the cluster like a boat docking at a pier. They fall in at hundreds or thousands of kilometers per second, carrying the velocity they accumulated, falling down the enormous gravitational gradient of a dark matter halo containing as much mass as a quadrillion suns. The cluster is perpetually under construction, perpetually accreting new galaxies from the surrounding cosmic web, and the infalling galaxies are perpetually colliding with the hot gas already trapped inside the cluster. RAD-BAARG is caught in exactly this process, at exactly the moment when its infall velocity has pushed it past the threshold where the gas cannot get out of its way fast enough, and the result is the bow shock structure the radio images reveal. When a galaxy falls into a cluster and its velocity exceeds the speed at which disturbances can propagate through this medium, the galaxy enters a supersonic regime. The physics of what happens next is the same physics that governs supersonic flight in an atmosphere, the same physics that causes a sonic boom. The gas cannot move out of the way fast enough. Instead, it piles up ahead of the moving object into a compressed front, a curved shockwave that sweeps outward from the leading edge of the falling galaxy. Astronomers have a specific name for this structure. They call it a bow shock, the same term used to describe the compressed gas that piles up ahead of Earth as our planet moves through the solar wind at speeds far exceeding the local sound speed. The bow shock of a galaxy falling into a cluster is the same physical phenomenon, scaled up by an almost incomprehensible factor. The arc illuminated by RAD-BAARG's jet plasma is not a coincidence or an accident of geometry. It is the direct outline of that compressed gas front, drawn in radio light for the first time with enough sensitivity to see it clearly. Here is where the key problem has always been. Bow shocks produced by infalling galaxies have been predicted by theory for decades. Simulations of galaxy clusters generate them constantly, but detecting them directly has been extraordinarily difficult because the compressed gas in the shock does not radiate strongly at most wavelengths. The best evidence for galaxy bow shocks before RAD-BAARG came from X-ray observations, where the compressed, heated gas at the shock front sometimes produces a faint X-ray edge. But X-ray evidence is indirect, statistical, and hard to interpret without an accompanying structure that makes the geometry of the shock clear. RAD-BAARG changes that. The narrow jet from the galaxy's central black hole is not just feeding its arc of plasma into empty space. The arc is being shaped by the bow shock directly in front of the galaxy, following the curve of the compressed gas like a tracer die injected into a flow. The radioplasma from the jet illuminates the shock from inside, mapping its shape with extraordinary clarity. The result is the bow and arrow structure that gives the galaxy its name, and that no previous radio survey had ever captured with comparable clarity. The arc is the bow, the jet feeding it is the arrow, and together they trace the exact geometry of the shock that has been building ahead of this galaxy as it falls through the intracluster medium at supersonic velocity. The reason the other side is twisted and asymmetric, the S-shaped jet and fading tail, is that the same intracluster gas that is being piled up ahead of the galaxy is also flowing past it on the sides and trailing behind, dragging and deforming the jet on the non-leading side into the distorted shape the images reveal. What this means in practical terms is that RAD-BAARG is not just an unusual-looking object. It is a natural laboratory for a physical process that has never been directly imaged with this level of detail before. The physics of bow shocks is well understood in principle. What has been missing is a clear observational example of it happening to a radio galaxy, where the jet structure maps the shock geometry for you in radio light. RAD-BAARG is the first clean example. Every measurement made of this object, its arc curvature, the velocity implied by the shock geometry, the asymmetry of the jet structure, is a data point on a physics that previously existed mainly in simulations. The discovery came from one of the most sensitive radio surveys ever attempted. The LOFAR 2-meter sky survey is a project built around LOFAR, the Low Frequency Array, a radio telescope network distributed across stations in the Netherlands and several other European countries. LOFAR does not look like the familiar dish antennas of radio astronomy. It is an array of simple dipole antennas, tens of thousands of them spread across hundreds of kilometers of European countryside, linked together electronically to function as a single telescope of enormous collecting area. The key capability that made RAD-BAARG visible is a survey's sensitivity to faint, diffuse radio emission at low frequencies. The arc of radio plasma illuminating the bow shock is not bright. It is extremely faint and spread over an enormous angle on the sky. Previous radio surveys simply did not have the sensitivity to detect it above the noise. LOFAR does, and the result is the clearest image ever obtained of this kind of structure. This sensitivity gap matters because it is the reason bow shocks like this one have remained essentially unobserved for so long, despite being predicted by simulations for decades. The predictions were right, the physics was right, the problem was purely instrumental. Radio astronomy at the frequencies where diffuse, old plasma glows most brightly requires extremely large collecting areas and extremely long integration times. Before LOFAR, those requirements were not met by any operational survey. The LOFAR 2-meter sky survey changed that, and RAD-BAARG is one of the first objects to demonstrate what that change actually means for what we can find. It is not that bow shocks are rare in the universe, it is that we have only just built the instrument sensitive enough to catch them reliably, and RAD-BAARG is the clearest example in the first large dataset that instrument has produced. But here is the part of the story that deserves equal time with the physics, because it says something about how science actually works in 2026 that the textbooks have not yet caught up with. RAD-BAARG was not discovered by a team of professional astronomers sitting at a major observatory running automated detection algorithms. It was found by a student on a hillside in the Himalayas named Pranim Limbo, working as a participant in India's RAD at Home citizen science project. RAD at Home has been training students, teachers, and interested members of the public since 2013 to search through radio telescope data for unusual structures, spotting the kinds of morphological oddities that automated pipelines often miss because they are designed to find what they expect to find, not what nobody has seen before. Pranim Limbo was doing that work, sifting through images, when the asymmetric radio structure of RAD-BAARG appeared in the data. She flagged it. The professional team picked it up from there. But the initial identification, the moment when a human eye looked at an image and recognized that something was fundamentally different from everything else in the catalog, that moment belonged to a citizen scientist looking at telescope data on a laptop in the Himalayas. This is worth pausing on, not as a feel-good story about inclusivity, but as a factual statement about the state of modern astronomy. The data volumes being produced by current surveys are too large for professional teams to examine by hand. LOFAR Sky Survey produces more data per night than any team of specialists can manually review. Machine learning helps, but it is trained on what has been found before, which means it is systematically less likely to flag things that do not match any prior category. The objects most likely to be overlooked by automated systems are precisely the objects most likely to be genuinely new, the ones with no prior category, no existing template. RAD-BAARG is exactly that kind of object, and the reason it was not missed is that a human being who had been trained to look for the unexpected was doing the looking. The case for citizen science in astronomy is not sentimental, it is structural. There are things in the data that will only be found by people who are curious, patient, and looking without a fixed expectation of what they will see. The physics that RAD-BAARG reveals has implications beyond this single object. Understanding how galaxies interact with the intracluster medium as they fall into clusters is one of the central problems of galaxy evolution, because that interaction shapes what happens to the galaxy on timescales of billions of years. The hot gas filling the cluster does not just produce bow shocks, it also strips material from the infalling galaxy, removing the gas the galaxy needs to form new stars. This process, called RAM pressure stripping, is thought to be one of the main mechanisms by which galaxies transition from star forming to quiescent, from blue and active to red and dead, as they fall into the dense environments of clusters. The faster the infall velocity, the more violent the stripping. A galaxy falling in at supersonic speed is experiencing RAM pressure at its most extreme. We see the end product of this process in galaxy clusters all the time. Clusters are famously dominated by old red quiescent galaxies, galaxies that stopped forming stars billions of years ago and have been slowly aging ever since. The field of galaxy evolution has spent decades trying to explain how that happened, how galaxies that were once blue and star-forming became red and dead, and RAM pressure stripping inside clusters is consistently near the top of the candidate list. But the mechanism is hard to constrain observationally because you are usually looking at the aftermath, the population of red dead galaxies that has accumulated over billions of years, and trying to reconstruct the process from the end state. RAD-BAARG offers something different. It is a galaxy that has not yet undergone that transformation, caught in the act of experiencing the conditions that will drive it. The bow shock geometry tells you the infall speed. The infall speed tells you the RAM pressure. The RAM pressure tells you how quickly the galaxy is losing its star-forming gas. And all of that together is a direct observational anchor for the models of how galaxies die inside clusters. RAD-BAARG gives astronomers a direct measurement of that process in action, because the shape of the bow shock and the velocity it implies allow the team to calculate the actual speed of the infall and the RAM pressure the galaxy is experiencing right now. Those numbers feed directly into models of galaxy evolution and into simulations of cluster formation. Every well-constrained observational example of this process makes the models more accurate, and more accurate models make better predictions about what the galaxy population inside clusters should look like, which in turn can be compared to what we observe across cosmic time. What the future holds for finding more objects like this is genuinely exciting in a concrete way, not just as an abstract possibility. The Square Kilometre Array Observatory, the largest radio telescope ever built, is currently under construction in South Africa and Australia. When it reaches full operational capacity, it will be orders of magnitude more sensitive than LOFAR at many frequencies, and will conduct sky surveys that make the current LOFAR survey look like a preview. The expectation among the researchers who discovered RAD-BAARG is explicit in the paper. With the SKA and with machine learning tools trained on objects like RAD-BAARG, bow shock structures like this one should move from near-invisible rarities to a documented population. What is currently a discovery of one could become a catalog of hundreds, and that catalog would provide the first statistical picture of how common supersonic infall actually is across the cluster population, and how much of the galaxy transformation we observe inside clusters can be directly attributed to the kind of extreme interaction RAD-BAARG is showing us right now. For the moment though, there is only one RAD-BAARG. One galaxy falling supersonically into a cluster, one arc of radioplasma 1.8 million light-years long, tracing the curve of a shock wave that theory predicted and observations almost never clearly showed. One researcher with 25 years of experience looking at something he had never seen before. And one student in the Himalayas who spotted something unusual in a dataset and flagged it for the team. That chain, from a telescope in the Netherlands to a laptop in the mountains to a paper published last week, is what the actual process of discovery looks like in 2026. The universe keeps producing things it did not ask permission to produce. All we can do is build the instruments sensitive enough to see them, the community is open enough to welcome the people who find them, and the scientific culture honest enough to say, clearly, that after 25 years, this one is new. We will be tracking developments with RAD-BAARG and the SKA as they come. If this video reached you and you want to follow where the science goes next, subscribe and hit the bell so you do not miss what comes after this. Drop a like if it was worth your time, and leave a comment below with the part that surprised you most. The citizen science angle, the physics of the bow shock, or just the fact that this thing exists at all. We read every one.